So in your notes, put projectile motion. I'm going to see, hopefully this will show up at home. I've got this little Canon app where all I have to do is hit fire and it'll launch the tank shell and it's trying to hit this target. It's a lot like what they would do with artillery. They would take like the howitzers and they'd shoot at a target. It could be miles and miles away, and then they'd look with their binoculars and see if they were a little short or a little long or a little left or a little right, and then they would adjust. Well, I was a little short here, right? So look at all the things that we can adjust in a equation for a parabola or for a quadratic. What do you think I should do? Any guesses? Yes. All right, you're right. Both of those could work. What do you want to do? All right, he wants to change the angle degree. Now it's 80 degrees now. If we made it 90 degrees, it would just go straight up, right? So what do you want to do? Let's go 70. All right, and we'll see what happens. Put in 70, and then hit fire. It's going to be too long, because that tell you, though, if you knew what 80 was, and you knew what 70 was, doesn't it logically follow? 75. And that's exactly what they would do. They would say, okay, that degree was a little too short, that degree was a little too long, and they'd try to adjust and get right between the two, and they'd be able to hit it. So this would be, let's say, 75, and hit fire. Look good? Yeah, perfect. Okay, so let's clear that off and then go back to 80. Let's say we leave it at 80. Let's say our cannon is stuck at 80. Let's do it with a speed. What do you need it to do? If the initial one, the first shot goes like this, what do we need to do to get our projectile to go a little farther? A little faster. So give me a number. What do you think? 25. If it is too high, you'd actually rather be a little too high, because then, look at that. We went perfectly too long, in a way, because now we know it's exactly between what and what. Between 18 and 25. And what is exactly between 18 and 25? 21.5? All right, let's try it. I bet you it's going to be right. And that's exactly what people would be doing out in the range when they're trying to hit the old car or whatever that they were using for practice. Got it. Okay. So one more thing I want you to think about. If the speed was also stuck at 18, I couldn't mess with the speed, then at least I could affect the mass, how heavy the thing was. All right, so let's change it to, what do you think, more or less weight if we want to go farther? Okay, so if our initial shot goes like this, you want less weight to have it go farther. So then let's try that. 110 I'm going with. We'll see what happens there. We changed it a fair amount. Fire. Did you learn something? Let's try it one more time, make sure that wasn't a fluke. Let's make it like 50. Well, 0, it might not even allow us to do that. Look at that. Same exact thing. That's the same idea as this. If I stand on the top of the Sears Tower, do you know where that is? All right. It's in Chicago. And I stand on top of that, and I throw off a bowling ball, and I throw off a marble. They're going to follow the exact same path. You'd think that the bowling ball would fall a lot faster. It doesn't. You'd think that the bowling ball might have like a steeper angle or something. It doesn't. If I throw it with the same speed, then it's going to follow the same path. Now here's the hard part though. Like if you think about it, if I want to get the bowling ball to be launched at 18 feet per second compared to a marble being launched at 18 feet per second, it's obviously a lot easier for me to throw the marble 18 feet per second. It doesn't need much gunpowder, if we're using this example, to do the marble. It just needs more gunpowder. But if you keep the speed the same, the speed was 18 either way, then it doesn't matter if you're launching a car or if you're launching a little tiny, like a golf ball or something. If their speed's the same, they're going to follow the same trajectory. All right, so I hope you learned something there. And next thing we're going to do, there's another just a little fun one that one of my colleagues, Mr. Johnson, found these. B-dubs. How many of you guys like Buffalo Wild Wings? Me too. Love the wings. Okay. And then they have this little game there where they have wing ball. That is a little, you're kicking a wing through the uprights, because this is, of course, Buffalo Wild Wings. So if you just like it, you get it lined up and it seems like it's just right. Oh, no good. Then I did this like 5 times before I realized what was going on. What could affect it? Wind. You got it. If you look really close here, you can see wind speed and direction 14 miles per hour to the right. So if it's blowing to the right, I got to aim a little bit to the left to adjust for the wind, right? So, oh, I had to aim too far to the left. Wind speed's still 14 miles an hour, so. I didn't go far enough left. They changed the wind on me. The wind was blowing the other way. Okay, so that's a projectile wing, I guess. All right, enough of that. Now, here are some things that you have to know. You have to be able to find the maximum height of your projectile. And that's like right here, and there's a name for that. What's the max height called? The maximum. And it's also called something starts with the V, the vertex. And where is it at a given time? Like they're going to a lot of times say at time 2 seconds. Remember, time's on the bottom here. So at time, let's say 2 seconds, say 1 second here. At time 2 seconds, where is it? Well, you can say it's right there, and you go over to the height, and you can say it's this high. And the last thing is they ask about these all the time. We in math are kind of obsessed with that spot and that spot. What are they? What are they in math? The roots. And the quadratic formula. Quadratic, I know. Quadratic formula tells you the roots. All right, but we've got a smarter way to do it today. Here is the equation, and it's pretty advanced. It includes a lot of factors. It even includes a factor for the gravitational constant. And that's because if you do a projectile on the moon, it's going to have a different equation. We can even adjust for that. So you can adjust everything in this. So I'd like you to write this one down, including all of the G and V sub 0 and H sub 0. This whole screen, I want you to copy it down into your notes. I'll pause while you do that. So as you are copying these things down, if we want it to be like Superman, all you got to do is go to a planet that's really small. Like the moon is an example. It's not a planet, but it's a small celestial body, and it has therefore not much gravity. And so if you went to an even smaller moon than that, you could run around really fast. You could jump really high. You could lift things that are really heavy, all because the gravity isn't holding you down. So the downside is, after a while, astronauts have found it, even in space, they have to get, their bones get really, really weak, and their muscles get really, really weak because they aren't used to having any gravity. And so there's like, you know, like even lifting your arms, you don't think about the work that is. That's actually hard work. You know, don't believe me, try holding your arms out like straight for like, 5 minutes eventually. That's a way that they actually use to torture people, because it hurts so much after a while just holding your arms out, just fighting gravity. So we don't have that working against you like out in space. Your muscles get really, really weak, and your bones also get really, really weak. On the other hand, if you were to move to Jupiter and live there for a few years, you could come back to the Earth and be incredibly strong, because you're so used to being pulled down by everything. And like when you walk, it was like, it'd be so much more effort. And because everything's twice as heavy, and you'd come back here and you'd feel like you're Superman. So for today, we're just going to use the gravitational constant, that negative 9.8 thing. We're going to use that for everything. So that, by the way, if I always have a negative 9.8 here, and it has to be negative because that way my parabola has a leading coefficient that's negative, you remember that? And that means that it's going to go up and like this instead of like this. All right, so the fact that we always start with that means that we'll always, instead of putting 1/2 and then a negative 9.8, you just put that all together and say negative 4.9 at the beginning of your equation today. That's going to make your life a little easier. All right, I'm going to stop the first part of my video here.